Welcome back. We were discussing on the link budget, and we have seen the C by N naught calculation in uplink and downlink, and from that the total C by N naught, which will be the quality that is required by the user. And this C by N naught calculation depends on the uplink power in terms of EIRP, and downlink power from the satellite, then the G by T of the satellite and the ground station, and the path losses or other losses put together, and Boltzmann's constant. This can be done in ratio or in dB, that also we have seen. And then we have seen, since satellite operates in the satellites are nonlinear, particularly the power amplifier of the satellite is nonlinear. So therefore, at some point of the input which is going to the satellite as a input power, we can call it a input power flux density. As you go on increasing, the output EIRP from the satellite will linearly increase first, and then it will saturate at some point. These satellite manufacturers, spacecraft manufacturers, they specify at what power flux density the output will be saturated. So this input power flux density they call saturated power flux density or saturating power flux density, SFD in short, and correspondingly what should be the EIRP maximum or saturated EIRP from the satellite available. These two specifications are given, but since that is in the saturation point and nonlinear, so therefore to operate in the linear region, to avoid the spurious which will be harmful, we go back in the linear region from the saturation point. So the input power flux density is reduced from saturated power flux density by few dBs, which is called input back off. Correspondingly, there will be output back off from EIRP maximum to the operating EIRP point. So we have also seen how to calculate C by N naught uplink and C by N naught downlink using these two terms, which is saturation power flux density and corresponding saturation EIRP or EIRP maximum, and for the operating point input back off and output back off also has to be known. And in that process we have introduced a new term, which is spreading, which depends on the frequency of operation. The spreading in the uplink and spreading in the downlink will be different, but we have seen a brief calculation with some small examples that what will be the corresponding numbers that will be appearing. Now in this geostationary, mostly we are talking about geostationary because you have seen that uplink and downlink path losses are quite large. So geostationary operation, we are operating in the environment where other satellite operators are also existing, on the same coverage area is being covered by other satellites. So there may be a possibility of interference. And since it is a natural resource, this interference has to be regulated properly. So the regulating body is the International Telecommunication Union, ITU, and most of the agencies, this spacecraft as well as the ground or satellite operators, let us say, they follow the guidelines which are given by ITU. So today now we will be discussing on this the interference and how much it can be tolerated. So for that, what can be done, that brief calculation, brief idea about that. So interference coordination. So as per the ITU, that is ITU regulation, the person who is operating has to tolerate increase of 6% receive noise temperature if it is operating on the same bandwidth. That is the tolerance. You have to live in a society, so you have to tolerate some people. There should be some toleration limit. So this is the limit given by ITU, So, single entry limit of interference should be tolerated up to 6%. Everybody has to agree on that, because they are sharing. So, there, it's a radiation pattern of a antenna which cannot be a straight rectangular. It cannot be just one single pinpointed focus to only satellite. There will be some radiation which will be falling to the nearby angles where nearby satellite may be there, and if it is transmitted from the satellite, a nearby ground station also will get some amount of power which will be falling into them, and if both are operating on the same bandwidth, it is acting as interference. So, therefore, that interference has to be tolerated. You can see from this brief discussion, it is the gain of the antenna is coming into picture. It is very important point. So, at which direction your station is from the satellite, which direction a station is pointing to the satellite, and what is the gain pattern, that really affects the interference. We will see into more detail of that, but first let us see this 6% thing. So, 6% if we convert into logarithmic, 10 log of this 6%, which is 0.06, becomes 12.2 dB. So, interference protection criteria as per ITU is the required C by interference, now I call. So, it is carrier power to interference is the C by N plus 12.2 dB. So, the C by I should be more than C by N by 12.2 dB. So, that should be your required C by I, but when you are actually operating, the available C by I will be maybe more than this or maybe less than this. If it is more, obviously your available C by I is more than required. So, you are in the positive margin, you are not interfering. If it is equal, then also it is tolerable up to 6%, but if the available C by I is lower than the required C by I, you are interfering. So, let us do how do you do this calculation. We will do it in dB, and we will draw simple picture so that you will get idea. So, let us see the uplink part. Let us see how do we calculate the C by N first. So, let us draw a satellite, brief picture of satellite with the solar panels. It is the antenna, and let us say there is a station which is uplinking, and there is a station which is getting the downlink. So, there is a one way is going on. Now, the characteristics of this, we are assuming here one thing, that since it is earth station, it is on the earth, you can perfectly point it towards the satellite. So, your antenna gain maximum is towards the satellite. So, it is gain maximum towards the satellite. Similarly, the station which is receiving, you can properly point it and leave it, it is a fixed station. So, its gain towards the satellite is in both sides. So, it is properly aligned, but the satellite antenna, whether it is transmit or receive, is pointing to the center of the service area, and from the center of the service area, these transmitting and receiver station may be a few degrees away looking from the satellite. So, the gain of the satellite towards this gain of the satellite antenna towards the uplink station is reduced from the maximum gain, and by the angle theta, of course, and similar thing is towards the transmitting station, that is in the downlink. So, those things we will bring into picture. So, let us term it. So, the power from this uplink station we call power of the earth station, maximum power, and when I say maximum power, it is power amplifier plus feeder minus feeder loss, etc., which is appearing at the at the satellite. This gain of the transmit station will take maximum. It is pointed towards the satellite, and the bandwidth is uplink bandwidth. And at the satellite, which is receiving from the uplink station, the gain of the antenna is reduced by theta, that is received satellite, and there is a, of course, the temperature, system noise temperature of the satellite, that is at the receiver of the satellite. So, you know that from the transmit side of the satellite, it is maximum power that is transmitted, P sat maximum. I mean, feeder losses, everything is included into this, but the gain of this satellite antenna towards the receiving station is from the both side, it may be different. So, I put the same angle theta. These two thetas may not be same, for that easy calculation we put same angle. So, that is transmitting from the satellite, and of course, the bandwidth of the downlink. The station which is receiving, he has a receive antenna gain, which is of the station, which is pointed, as I said, since it is on the ground, and the temperature of the receiver station, TEX. So, in dB, if I write it, C by N, instead of up I am putting upward arrow, instead of down we will put downward arrow. And of course, there are two more things we skipped. Let us write the loss, which is all these days we are writing path loss. Here I am introducing this new, because in many books it is written in other form. To get yourself familiar, I am writing free space loss, which means the same thing. It is the path loss in the uplink. In some of the books it is written free space, and you will be wondering what is this free space. So, it is a free space loss, same as path loss. So, free space loss uplink and free space loss downlink. Okay. These two are different because the frequencies are different. So, C by N, you can call it C by N naught or C by N. If we get C by N, bandwidth has to be taken care. So, C by N uplink is the power of the station maximum power, which is transmitted from the station, then the gain of the transmit station maximum, which is pointed properly, and the gain of the satellite antenna receive with the angle theta, g theta it is receiving, minus the free space loss, which is path loss, the uplink, and minus the Boltzmann constant, the temperature, that is the system noise temperature of the satellite, and of course, the bandwidth, because we have taken C by N. So, these all are in dB, that is why you are seeing plus and minus. So, similarly, C by N downlink will be from the satellite. So, P satellite maximum plus G theta transmit from satellite plus G receive station max. These all the G's are gain of the antenna minus the free space loss in the downlink, which is nothing but downlink path loss, minus K the station noise temperature, system noise temperature, and the bandwidth. Fine. So, therefore, the C by N total, or simply C by N if you can call, is, we know this expression. This is in the uplink and this C by N in the downlink, and this you remember that is in ratio. we calculated these are all in dB. Here we are doing terrestrial. And then you remember this C by N total what you calculated is 12.2 dB. If you add, then you get the required C by I. Okay. So, this calculation we should do to find out what is the required C by I, but then you have to find out what is the available C by I. Let us do that calculation quickly. It's pictorially, it is much easier, isn't it, when you do it pictorially in dB. So, let us do some basic C by I calculation. Basic C by I. So, for the uplink interference, let us draw the satellite again. Now, there is a station which is uplinking towards the satellite, pointed the antenna towards the satellite, free space loss, uplink. So, it has power of a station which is maximum and gain of the transmit antenna which is a station maximum. This is the wanted link. This is the wanted link, and there is another station which is interfering. This is interfering station. So, it has the same frequency of operation, same bandwidth, it is interfering. So, free space loss will be more or less same, but depending on the range it will vary. So, interfering station let us call by prime, FSL prime uplink. So, this power prime of the station maximum, and G. Now, since it may not be co-located, it may be slightly away, it is actually working with another station, wanted station, another satellite which is wanted satellite for this station. Now, some of the gain is interfering. So, it is pointing to its own satellite of operation which may be nearby. It is pointing towards the own satellite of operation which is nearby. A G phi of that gain at a angle phi is appearing as interference. So, we will call G phi, G dash, because it is interfering at a angle phi is the transmit station. So, that is interfering, and at the satellite when it is looking, since satellite might be pointing, both side might be pointing, satellite antenna might be pointing at a both side which is theta degree away from the wanted wanted station. So, we will call G theta receive satellite, and here we call G theta dash receive satellite. It may be slightly different angle. So, the carrier power in the uplink is from the wanted station, that is PS max plus G Tx a station max plus the satellite G theta receive satellite minus the free space loss in the uplink. This is in dBW. And what is the interference in the uplink? I is from this side, that is P dash a station max plus G dash phi transmitter station plus G theta dash receive satellite minus FSL prime uplink. This is in dBW. So, your C by I uplink will be C uplink minus I uplink. This is in dB. So, it is easy to calculate. C separately you calculate is power and gain and the receive antenna gain from the satellite minus the free space loss or path loss, and interfering station power you calculate, which is interfering power. So, it is P dash, G dash and G theta dash from satellite and free space loss dash from satellite, ratio of that, or in dB subtraction of that. Similarly, downlink interference can be calculated. So, downlink interference from the maybe from a nearby satellite. So, there is a nearby satellite. So, we have a station here. This is the downlink free space loss, and this is the G receive station max, because this is the wanted station and wanted link. So, it is properly pointed, but it is from this satellite you have P satellite max and G theta transmit satellite, it may be theta angle away. From the interfering station, the interfering link which is coming, it has a free space loss prime downlink. So, it is P dash satellite max, P dash because it is interfering to the downlink, and it is G dash phi transmit max from the satellite. It is interfering, this is interfering satellite. This is the wanted satellite, this is the interfering satellite. So, wanted link, interfering link. So, C downlink is P satellite max plus G theta transmit from the satellite plus G receive or station max pointed minus FSL downlink, and interfering power I is equal to P dash satellite max plus G dash phi transmit satellite plus G theta dash receive at station minus FSL prime. So, C by I downlink is C downlink minus I downlink in dB. So, C by I total is C by I uplink inverse and C by I downlink inverse. This is in ratio, and then you can convert back to dB. So, this is the basic calculation of the C by I, basic calculation of the C by I, what you have done, what is really amount of power which is interfering in the uplink and downlink and total C by I. But then there is some bandwidth interference, how much bandwidth is really overlapping, interfering bandwidth is really overlapping on the wanted bandwidth, that also has to be considered. So, let us see that we do a bandwidth adjustment factor. So, that is done like that, is called frequency or bandwidth adjustment factor. That is nothing but that wanted bandwidth to interfering bandwidth, it is a ratio adjustment. So, let us take a case, first case, where that bandwidth which is interfering is larger than the bandwidth which is wanted. This W stands for wanted, I for interference. So, this is larger and it may fully overlap on that. So, let us draw it. Let us say this is my wanted bandwidth. So, this is bandwidth wanted, and the interfering bandwidth is coming over this and which is larger. So, this is bandwidth interfering. Now, you see in this what is happening, that the whole thing of my wanted bandwidth is getting interfered. So, it is called bandwidth overlap. So, interfere bandwidth is fully overlapping on that. So, in that type of case, that is where the bandwidth wanted is less than bandwidth interfered, and bandwidth interfered is fully overlapping. The overlapping part has to be seen, is fully overlapping. Then this interfering ratio adjustment, which is termed as IA, is 10 log of bandwidth overlap by bandwidth interfered. How much is overlap? That is fully interfered bandwidth is fully overlapping on that. So, PW is also equal to, I mean these two are fully overlapping, we can take both of them are same. Sorry, they are not same, they are bandwidth interfered is more than that, it is overlapping. Wanted bandwidth is fully overlapped with interfered bandwidth. So, in that case it is the 10 log of bandwidth wanted by bandwidth interfered, which is bandwidth interfered is large. So, this is a fraction less than 1. So, this will be a log is a negative quantity, this is negative. There can be another case where it is partially overlapped, case 2, where bandwidth interfered is less than bandwidth wanted. Let us draw it. This is the bandwidth wanted, and this is the bandwidth interfered. So, in that case, that frequency adjustment factor is 10 log of bandwidth overlap by bandwidth interfered. Overlapping is only in this region. So, it is 10 log of bandwidth interfered by bandwidth, whatever bandwidth interfering is the same as bandwidth overlap. So, bandwidth interfered, which is equal to 1, which is equal to 0. So, C by I available is C by I basic calculated minus interference adjustment factor in dB. So, C by I available is equal to C by I required plus margin. If this margin is greater than or equal to 0, no need to coordinate with the operator which is interfering. But if margin is less than 0, then there is a need for coordination. And in this game, that is first come first serve, whoever has launched the satellite first, he has the more right, and some new satellite operator is coming to operate nearby region or overlapping on that. So, that satellite operator has to coordinate with the original existing satellite operator and find out what is the C by I he is getting from them and how much it is interfering with them. And so, that 6% is only tolerable, and therefore, he may have to adjust his gain of the satellite, the antenna pattern, gain of the earth station and antenna pattern, or he may have to readjust the frequency band so that overlapping is much less. So, actually it is power flux density which are adjusted. So, with this let us conclude the link budget. I tried to give you varieties of information and very quick calculation how it can be done and how the interference are calculated and what is to be done with the interference, like that is the coordination in the GSO scenario. A similar thing in other satellite scenario also can be done. Thank you very much, and next period we will talk about the medium, that is through which the satellite signal is passing through, the impairment and mitigation techniques for that. Thank you very much.